All right. Hey, everyone. So we are here in week 5, and you should have just watched the quick video notes about proteins and enzymes and some of those definitions like enzyme and substrate and what enzymes do. So this simulation here is going to show how enzymes can depend on another factor. So in our body, we have millions of enzymes that do different things. They help us break down foods. They help us connect our brain to our muscles to help us move. They speed up chemical reactions so that we can do things like move our leg the instant we think about it. And they also control things like adrenaline release. So if you get nervous and your legs start to go numb, those types of chemical changes all require enzymes. Most of the enzymes in our body are specialized chemically. They work at a very, very specific temperature. And so this simulation is going to show us how that temperature impacts what an enzyme does. So in the model, we've got our pink enzyme here, and it shows that it's got this square cutout in the middle, and we can fit that substrate right in there. Down at the bottom, I have my temperature slider, so I can go from low to high temperature, and we're going to kind of increase it slowly. And over here on the right, this is kind of the part that we need to focus on, which is the actual graph. So on the x-axis, temperature, cold to hot, and slow to fast on the y-axis, up and down. So the faster the reaction goes, the higher up it's going to go. The hotter that the enzyme gets, if we raise the temperature, it goes more to the right. So let's start and see what happens. So I'm going to start, and I'm going to let it go at a pretty cold temperature. And we see the substrate start bouncing around, and they lock into the enzyme. Lock into the enzyme. And if I start increasing the temperature even more, we see over here on the graph that the substrate starts actually getting broken apart faster. So we got hotter and it got faster. So let's go even a little higher, a little bit warmer. That enzyme, they're all moving faster, they're bouncing around, they're getting reacted faster. Let's go even hotter. See the background's getting yellow. Now the substrates are everywhere. And look at our graph. It's starting to kind of take a turn. That's kind of odd because the hotter we got, the faster the enzyme broke apart our substrate. So if we keep getting hotter, we would predict that the enzyme should keep working faster. So let's see if that's true. I'm going to get really hot. Oh! Uh-oh. So I'll slide it all the way to the end.
Denatured.
And denatured actually means that the enzyme died. It broke apart, it fell apart. It wasn't really alive, so it didn't die, but the enzyme fell apart. It got too hot for it to work. So let's look at our graph and talk about what that might actually mean. If we look at the graph, we can see that there's a peak or kind of a mountaintop in our graph. And that mountaintop happens somewhere between cold and hot. So let's say if cold was 0 degrees and hot was 100 degrees, the enzyme actually worked the best at about maybe 60 degrees, just past the halfway point between cold and hot was where the graph was the tallest. But anywhere too cold or too hot, the enzyme didn't really work that well. And so a graph like this one would help us show what temperature an enzyme works best at. A lot of the enzymes in our body work at 98.6, which is Fahrenheit, which is our body temperature. So the key takeaway for you is that you need to understand that enzymes are most efficient at specific temperatures. If you get too hot, that enzyme protein falls apart. If it's too cold, the enzyme doesn't work very fast. So there's an ideal or optimum or best temperature for every enzyme. And we can figure that out by creating a graph of rate or speed versus temperature. And the highest point on the graph is where our enzyme is effective, which in this case is between hot and cold.